Great. Thanks for having me. So I'm going to talk, I think it's really nice following Gilles' talk and kind of looking on both of our backgrounds, or we both kind of made this journey a bit coming from a background in, let's say, somewhat non-conventional architecture and then moving into the startup space. So I'm at a company called Gravis Robotics. We do autonomous heavy equipment. And I'll talk today a little bit about my journey, which again went kind of from that architecture landscape toward now being in autonomous earth moving. And if I kind of rewind a little bit and think about how we got here, it was a bit in that kind of early exposure to kind of digital fabrication, the excitement about computational design, very popular when I was in undergrad. There were a lot of these, fantastic buildings being made in the early 2000s where, there was a lot of effort in essentially saying that, design could allow us to build the most complex geometry. Anything you could imagine could become real, right? It was very much this dream of the 90s. Whatever you can dream can become real. And then there was so much effort that went in companies like Gary Tech and design to production in kind of the computational rigor behind those geometries to be able to bring that material complexity into the real world. It just so happened that, I came through my undergrad learning all of this stuff, very, very excited about the kind of, the Starchitect spirit, and went directly into the 2008 financial crisis. And the kind of the reality of the built environment, and seeing that, this kind of tabula rasa approach to architecture, this kind of beautiful, sprawling buildings that looked like someone did a napkin sketch and then materialized with, significant production waste and cost. And then you compare that to the kind of the environmental challenges that we have, and also the financial challenges of the time, and made me start thinking a little bit about how can we maybe rethink this to be a little bit different. And I think, around that time, you started seeing a lot of really amazing work looking at a kind of very kind of foundational level, very handcrafted design around using irregular materials, non-standard materials. Things like Rural Studio building this beautiful glass facade that looks like a Gehry facade, but it's a bunch of windshields from a car bolted onto a steel frame built for a few $100s because of, scrapyard pricing. And just the kind of, the kind of beauty that comes from these kinds of geometry built out of reclaimed materials. And I think if you compare these two projects, like both, there's a lot of merit in both. There's a lot of variation. There's a lot of kind of nuance between these materials that you have these individual components of the buildings where everyone is a bit different, but there's some kind of spirit to this kind of this craft of stonemasonry that is lost in this kind of very repetitive, very grasshopper looking geometry that comes out of computational design. And then as we're kind of going through the last, let's say, decade or so of technology, you started also having a lot of new innovations in robotics, right? So you start having robotics that are coming out of the factory, that are going into the real world, and they start understanding the complexity that is operating in the real world, right? You're exploring tunnels. This is actually the lab that I did my PhD in. We won the 2 million DARPA Sub-T challenge. But you're looking at these big challenges around cave exploration, around unpacking and packing shipping boxes, around actually doing construction and search and rescue tasks with robots. And that kind of, gradually clicked, and I'll get there in a bit talking through my own work. But, can we, rather than taking that idea of computational design as letting us materialize computational complexity, can we turn that on its head through approaches like this and actually get robots to help us materialize or rather like manage the complexity of the material world as it is, right? The world is already a complex place. Do we need to introduce more complexity to the world, or can we actually get robots that help us understand and efficiently use that complexity as it is? And so if I reflect, kind of looking back again, I think at this evolution, of the kind of the master architect to what we kind of knew for a long time as kind of division of trades between architecture, engineering, and construction, and how digital fabrication kind of changed a little bit that equation, and that we're as computational designers, we started working together with CAD, together with simulation, handling much of the engineering complexity, and then added in kind of robotics to be able to work across these three worlds. That was, to me, very much the spirit of the kind of digital era. But in the kind of thought about how we approach this conversation, like what does it mean to be post-digital, to be able to blend these kind of worlds in a different way, I think what happened is there was an explosion of complexity that came out of those fields, right? So we start not just looking at little fabrication projects, but needing to bring in expertise from material science, expertise from, kind of virtual reality and augmented reality, human-computer interaction, Internet of Things, 3D scanning and surveying. All of these technologies kind of become a very complex web where, as an architect who's trying to design something that's efficient in this post-digital world, it's very, very difficult to kind of find your way through this web. A lot of new possibilities of how you can craft a career in essentially finding, 4 or 5 of those nodes and connecting them in your own way. But if you're kind of new to the field, I think there's a lot of challenge in specifically how we navigate these post-digital design constraints, which come from many, many different spectrums. So I think, what I want to talk about today is really just how my own career started to try to navigate through these different things and get to where I am with the work that I'm doing now. So one of the core fascinations that I had when I started looking to robotics was, that latency that happened between when you designed a building in CAD and you needed to then materialize it. There was this process of kind of freezing a design and then creating a bunch of files and then executing them. And what it felt like was missing is the ability to kind of design through materials by kind of tightening the amount of time between that design process and that fabrication process. So in 2011, I spent some time with Gramazio Kohler. The Connect had just come out, and it was an opportunity where basically we set up an industrial robot, not just to build a brick wall from CAD, but to build a brick wall which was actually just gestured by the hand, right? It would kind of track my skeleton and then build the geometry exactly where I wanted, and it kind of created this immediate link. But even then, there was still this kind of binary divide, and I spent a lot of effort. This was before, we had all the wonders of AR that we have today. This was a first-generation Android phone with a one-way mirror on it that would essentially track where I was looking with the Kinect. And it was a very, cheap augmented reality headset, but I could still use that Kinect to draw out geometry and then kind of materialize that with ways to edit that and kind of work directly between that kind of robotic fabrication space and the kind of 3D world that I was designing in. But even still, it felt like, I was trying to drive more and more at how can a person get into the loop with a robot. So I set up, a number of different projects. This was with a tablet where the robot would go and mill geometry. It would show you where it was going to go, but you could kind of modify where it would mill just by tapping on the screen. So the idea is here's, you're creating some geometry and there's an area that you really need to get done. You can just tap on the screen. The robot will go there and do that work, right? So starting to really make even that process of following a tool path something that is ad hoc and done online. And all of these screen-based experiences are also very individualistic, very kind of personal. And I also wanted to know how could you bring those things out and share that information with others. So I was looking into things like projection mapping, where here, I'm sure you're familiar with projection mapping. This was a very novel take on it. So we essentially took a projector and we bolted it onto the back of a robot. And you can imagine this as like a virtual reality flashlight. That shines. I'm being told to speak slowly. Sorry, it's not something that I'm very good at. I'll try. So you have this essentially this virtual reality flashlight that's shining geometry onto the wall, and this is done by essentially taking a 3D scan of the environment, taking the 3D scan from the LiDAR that's on the back of the robot, and using that to locate the robot into the room. And if you locate the robot into the room, you can essentially know where the projector is, and you can put it like a virtual camera in a virtual copy, so a digital twin of that world. And then you can essentially play what that virtual camera sees back onto the real environment, right? So as this robot walks around, you can see the kind of the original indication of those lines. So we had students come and they could draw geometry onto the wall, and they could immediately see that kind of painted wherever this robot was looking. So taking away the headset and putting it into the hands of many people. And I think that opens new opportunities for collaboration. All these devices kind of open different ways of us working together and seeing how robots work. They can even change the way that we can do things. So a lot of my work is around getting robots to do things, but we also did a lot of work in looking at how can the way of showing information get people to do things. So this was a very silly kind of video game where you would go to a zoo and there would be an elephant, and you could grab its trunk and you would go and vacuum to feed it peanuts. And if you collected all the peanuts, then it would be a happy elephant. We learned only later that elephants don't eat through their nose; they kind of eat through their mouth. But basically, what you would do is you would take this away, and you would actually see the 3D geometry that was underneath, right? So you would actually kind of use this vacuum to create a very precise 2.5D surface by kind of just playing this game of feeding an elephant peanuts. And all of this kind of helped kind of understand how to work between that 2D and 3D space. But still, I felt something was missing from that understanding of the material world, because as we started to work with robots, we found that their ability to control, let's say, space and time allowed us to work with materials in very unique ways, right? So the robot might follow a very simple path, but you end up with this very complex interwoven material. And I wanted to understand, is there a way for us to help, through kind of software and through simulation to help us design more fluidly with such complex behaviors? So rather than taking a design, going through software, translating that to a machine, and then getting to the material result, can we essentially short circuit that gap and get us closer between design input and material? So my master's thesis at Princeton was something along these lines, where you had these purple blocks. They would represent a structural load, and you could put them down by hand anywhere along this top of this black wax block, and it would create a simulated load that would go through from where you put that block. And I would run this through topological optimization, which would run online. And I had this also bought from an old car factory, an old robot that would go and essentially melt away the areas that weren't performing structurally. So kind of this very collaborative design between myself and the robot, that I could move this block. I could also color on the surface here to say anywhere that's green, I wanted no material. And the robot would see that green color. It would kind of recalculate around that and then proceed to melt away the areas that weren't performing. And so over time, this process kind of would evolve this very collaborative, drippy material that wasn't really exactly my intent. It wasn't exactly the structural intent. It wasn't exactly the kind of organic nature of the wax, but it was this kind of hybrid collaboration between all of those different parties. And I think the other thing just to mention is that here I'm also tracking my head, so that projection is matching where I'm looking, is how that kind of works. And you would end up with these very kind of grotesque forms, right? Something that didn't look modeled by a computer. Very difficult even today to model something like this on a computer. But we could essentially mix those very complex material behaviors with that kind of desired intent. So here, I talk a bit about this kind of four-way collaboration. There's the person who's in a way kind of deciding, does it look good? Does it perform well? So the simulation is being that kind of structural calculation, and then the robot is there as a partner to help kind of precisely materialize that design. I went on to kind of teach exactly this approach at Princeton for a number of years, where students did all kinds of crazy stuff with different materials, things like playing with caustics of light, where you could paint with your hand and then see the geometry unfold on the wall by having motors control very irregular mirrors. Or here, for example, shaping with your hands exactly how you want a sheet to be shaped, and then using PID control on fans to basically keep that sheet in exactly the shape that you want. So kind of letting these computational tools help us harness that complexity of the physical world. And then, as I worked through this, and I kind of thought, how do I bring this back to the architectural scale, right? These experiments are all quite small. What is the thing that makes kind of this non-standard material possible at the architectural scale? And a lot of that was that, architecture is built, as you saw in the last presentation, from pieces. Can we take that complexity and those non-standard materials and build much like, the historic builders and the craftsmen built out of those individual pieces? So I did a number of projects around this in my early work. This was, for example, a chair where we would scan a piece of wood as it grew and then come up with a special algorithm to essentially fit and nest a complex doubly curved surface with zero waste into that shape, right? So this chair essentially exists only as a possibility within this specific piece of wood, but that because of that control that you have over the robot to be able to cut and extract and then nest these materials in an efficient way, we could start to get very complex geometry out of kind of natural components. Again, like using robots here for things like assembly, 3D, 2D scanning objects and then building structures, then planning how they fit together. And then also looking at that ability to communicate. So this was at, I think, actually the same Seoul Biennial that Gilles brought up in a presentation. What was it, 2017? Okay, a different year. So here, basically, we had this exhibit where people could bring trash from their pocket and they could give it to the robot and it would scan it, it would try to pick it up and it would build something out of it. And if it was too porous, it would sense it and it would make an announcement. This is too porous for me. If it was too heavy, it would drop it and it would make an announcement. This is too heavy for me. And so people started to not just know, hey, I can use this robot, but they started to understand that it was limited. And if you understand the limitations of something, you all of a sudden have a lot more freedom in what you can design with. And I think the best example of that is this French artist, Hubert Duprat, who found this caddis worm who builds these little cocoons out of stones and sticks that it finds. And he understood what's the size of thing that it can pick up, what's the weight of thing that it can pick up. And he put them in a little bin with just gold and turquoise and saw that a whole new design language could emerge by understanding the way that this little worm could build things. And so I think that when we look at robots helping us build things, if you just understand what they can and can't do, we all of a sudden open a new language of design and expression. And various kinds of things using the same approach here, building with broken glass or broken tiles. A lot of my students did crazy projects sorting gummy bears by flavor, or understanding to take these vegetable straws and kind of stack them to where they fit exactly a line that you've drawn as a kind of simulation of building with irregular timber. And also looking at other ways, other kind of waste products that exist in the world, and how we can take that irregularity and bring it into building. So looking at a brief foray into timber-based assembly. I was fixing an old building, my own kind of house in New York, and I had a lot of wood that was very poor quality. And I set up a camera to essentially 3D, to capture the 2D length, width, and texture of each of these boards. You see here the sorted set of scanned boards. And then I set up essentially an algorithmic approach, which would take those lengths, take a design, and then use a genetic algorithm to essentially solve for a geometry that used that combination of lengths, that would sort those boards by their length and fit it and kind of essentially make whatever shape would be possible with exactly that set of material. And then to make that possible, I set up a routine which would then take that scan geometry, again using that projection mapping. You'd put the board down, a camera would recognize the board and then project onto the board where I needed to go. And this is a little handheld printer, like from an inkjet printer. And I could move that to the projected marks, and it would essentially show and would put the little crosshair where I would need to drill to then be able to build that structure. And then as you see here, I'm moving along, it's actually sending the message of the number of board that each of those holes connects to. So I'm projecting that information to give a rough guide, and then this handheld printer is essentially showing me where I need to drill. So this print message just says above board 93, above board 87. And then on each board there's a number, and when I would go to assemble, I could find then how these different numbered components fit together. We exhibited a version of this at the Hong Kong Biennial in, I think it was 2019. And then, it kind of really just kept working in this space, heavily with kind of 2D computer vision type approaches, recognizing blobs, understanding geometrically how they fit together. I did a project with Adidas looking at shoe assembly. So here you have a robot. This was a custom needle gripper that could essentially find bits of fabric that would be sorted by type and fit them together into a kind of upper footwear kind of assembly. So it would look at the stresses and strains of the shoe. They had these models of how athletes' foot kind of moved and where the shoe needed to be rigid and where it needed to be flexible. And so if you sorted these materials by type, this algorithm would essentially try to fit the stretchy materials in the stretchy part of the shoe. The robot would pick them up, put them in place, and then they would essentially kind of adhere them all together to be able to produce a shoe. This was a kind of prototype concept I haven't seen in a shoe store yet. So this was a lot of the body of work leading up to my PhD, which in the end I ended up doing at ETH Zurich on the topic of kind of dry stone assembly. So really taking that two-dimensional complex material assembly and scaling it up to the very, very large scale while adding in that kind of three-dimensional variation that stones allow. This was a great opportunity for me to get in with a group of people who were working with very large-scale robotics. So at the Robotic Systems Lab, we're basically taking learning-based control and applying it to this massive legged wheeled robot. You can see here the scale comparison really opened up the possibility of doing on-site architectural assembly. We outfitted this with a number of cameras and LiDARs over the time that we were working, and essentially used this as a kind of mobile robot to be able to do large-scale construction. So I'll talk a little bit about how this process worked. Essentially, we would use the camera and LiDAR to recognize rocks in the scene. We would take a 3D scan of the environment. You would be able to detect and classify that this was a standalone cluster or an object. And then we would plan how to grab that object with this gripper. So finding a way that you could grab that without colliding. You would then pick that stone up and spin it in the hand. And the LiDAR on the cabin of the machine would then do a 3D scan of that stone. So while you were holding the stone, you would kind of inspect it just like a stonemason would kind of look to understand that object. You would create the kind of mass and geometric properties of the stone, and then you would just put it back. You'd put it back down on the ground, scan it again to understand where it was, and then add it to a virtual inventory. And that whole process kind of looked a little bit like this. You see here the point cloud representation of the stone. You segment out where the stone is. You come up with grasp hypotheses to understand where you should grab it. You pick one. This was through also a learned classifier. You pick up the stone at that point, and then you see here as it's lifting up the arm, you can see those LiDARs that are on the cabin, which start to kind of scan that stone as it's spinning around. So you collect a series of points because you know where the arm is. You can rule out the points that belong to the arm itself. You create a mesh using Poisson reconstruction. You extract the mass properties as well. And then the other thing that we did here is that we would kind of understand not just the kind of volume properties, the center of mass, but we would also collect pictures as we scanned that stone. And by collecting those pictures, you could also do a photogrammetric reconstruction of that stone, understand where that photogrammetric reconstruction was, and then back project that onto this Poisson reconstructed mesh. It's probably very hard to translate, sorry. And then you would get essentially a textured reconstruction of this stone. And then I came up with a number of other algorithms which would help the kind of the geometric planar, where I would extract these kind of planar surfaces of the stone to describe what are the edges of the stone, what are the faces of the stone, and then this would help jumpstart this solver to understand how to fit that stone into a wall. We would put the stone down on the ground, let it go, and then rescan, and then update the placed position of that stone to match that scan. So every time we touch the stone, if we pick it up, we put it somewhere, if it settles a little bit, we would use that LiDAR scan to refine where it was. So we always had a very accurate model of this wall as it was being built. So once we had that, we would come up with kind of placements of where we should put the stone. I'll get to how we did that in a second. We would try to grab the stone. If we could grab it, we would essentially refine where it was in the hand, place it in the wall, and then if we couldn't find a grasp, we would then need to reorient the stone. So we came up with an algorithm which would find the stone, turn it over, and then grab it to put it in the wall. So as far as understanding where the stones fit into the overall wall, we had a method that essentially took an input and tried to fit stones inside of that. And the way that looked was, you can imagine having a virtual cage that describes the outside of how you want the wall to look. And you could give it any arbitrary surface. And we would use that virtual cage to define a center wall and also a closed volume. So this is kind of an imaginary cage you're trying to fill. And if you take a line along the top of wherever the current top of the wall is, I would create then almost like, imagine flying a virtual drone along this line and creating a point cloud scan of the top of the wall. Once you have that scan of the top of the wall, you can then create a mesh surface that represents that top of the wall. You can intersect that with that closed volume to then get a closed area, which is where you're trying to search. And the nice thing about this approach is that it doesn't matter if some of the area is the ground and some of the area is rocks. It creates one defined closed area which you're searching within. And then we would also find this kind of perimeter along the edge, which would be essentially where you wanted to place stones as you were building that structure. So as a mason, as a person building a stone wall, you typically want to put stones at the intersection of other stones. It creates this overlapping pattern which adds strength to the wall. So these places would be the kind of hypothesis locations of where those stones would go. And as I mentioned before, when we scanned the stone, we would also find the edges of the stone. So we would align those edges, and that would give us a kind of first initial guess. There was a bunch of other steps in there as well. We would essentially use a feature descriptor, so a learned kind of classifier of this local shape. We would match it to the local shape of the wall to find very good guesses of how those stones should fit. You would then get a bunch of candidates which would be roughly aligned, but not perfectly aligned. And then I used a custom algorithm which would essentially combine physics and geometric registration to pull those stones into a stable position. So if you just left them there, they'd probably fall off. But by kind of having this optimization problem, which would gradually pull the stones into alignment, where there was a reward if they were stable, there was a reward if the front of the stones were nicely aligned with the structure, this optimization would essentially take those candidate stones and turn them into stable, feasible solutions. But even with those solutions, you had the challenge that there's a lot of intelligence around how a stonemason builds a wall. It's not just about having one stone be good. It's about having a consideration of what will that stone do to the next stone. And there are a number of rules. For example, you shouldn't have this very small contact. You shouldn't put a stone where the top slopes out of the wall, because if you put the next stone, it'll fall out. You also shouldn't have stones that go too far to the other side, because if you do, there's not space for the next stone. The problem is, and at the beginning of my PhD, I did all of this very classically rule-based. So I would put these rules in and say, this is a bad choice, throw it away. But there's always exceptions. There's many, many exceptions to these rules where it's okay to have a stone that goes to that edge as long as it creates room, or it's short, it gives room to the next stone. So to solve this problem, I used a learning-based approach. So I essentially allowed the algorithm to self-build hundreds of walls in simulation. And then I created the world's most boring video game that essentially would let me rank stones as good or bad. So I could look at a choice and I could say, yes, this is an okay choice, this is a bad choice. And that allowed the system to essentially learn to classify good choices from bad choices. I would then feed that into, I represented these as what's called a signed distance field, and then ran that through a classifier, which then did a very good job of essentially learning which of those shapes was a good shape or a bad shape. And then I could lead this thing to just generate quite stable walls, fully on its own. So just leaving this without any need for intervention to create these candidates. Using this approach, we built a number of walls. This was the first one we built in Switzerland. Even though these are very big, these are 1-ton boulders, we were able to show about 10 centimeters of tolerance between these boulders and that desired target surface. So it's a relatively high accuracy for such a big structure and very irregular materials. The second wall that we built was about 3 meters high, 10 meters long. It has 110 boulders and pieces of irregular concrete. You see here also really a slender profile. So even as a person, it'd be very hard to build a structure like this, about 3 degrees taper. And you see here also that mix, this kind of very nice mix of different material types. This is just, you see here the construction sequence. So we were on a concrete recycling yard, which had access to a bunch of different pieces of broken staircases and cores of, drilled out from buildings. Really a wonderful set of materials that we could use to build from. And you see here in the background this massive mountain of waste, right? So really taking those waste materials and creating, I think, much like that image of the kind of historic stone walls, a very nice kind of material awareness and understanding here because of that mix of materials. Toward the end of my PhD, we built a wall with about 1,000 1-ton boulders. 6 meters long. You see me there for scale. It was 65 meters, 6 meters high and 65 meters long. And what was kind of remarkable about this is that as we built this stone wall, we had a scan of every single stone that we placed, right? So we have probably the most accurate model of any stone wall that has ever been. And you see here, this is the final wall, but that there's this very clear, close correlation to this 3D model. So very, very strong embodiment of the digital twin. But what was remarkable about this is it's quite a big wall. It's very large, has lots of boulders in it, took a long time to build. But if we account for even the fuel consumption and the fact that this is much bigger than the same structurally performing concrete wall, which, this wall's, more than 1 meter thick, and a concrete wall maybe would be 10 centimeters. If you look at the embodied carbon that is emitted from producing that concrete versus the carbon from burning the diesel and using these stones, we can actually build significantly more sustainable architecture by passing that intelligence on to the system, right? So I think it's intuitive for everyone. You're going to use less carbon if you build a wall out of stones, but we don't build walls out of stones because the labor is expensive, because it's a very complex job, very, very difficult to do, and robots unlock a new way of building, which gets us closer to materials and makes us able to kind of work more efficiently with those materials over time. This wall also was featured, I'm quite proud, in this year's Guinness Book of World Records. It's the largest stone wall built by a robot is the record. It's a very random one. This is me so I can now say to my kids that I'm in this book. And what was nice about this project is that we combined my own PhD work on stone assembly with the work of now my co-founder, Dominic, who was doing robotic-based excavation. So you see here the terraces around were actually also dug by the excavator autonomously. And we took that technology and we essentially brought it, that was evidence to us that this is technology that can work in a real construction site. Can we take this and bring it into a kind of more industrial, large-scale application? And we did that as a company that is now called Gravis Robotics, and we essentially do autonomy for heavy construction equipment. We do mainly things like truck loading, bulk excavation. There's more than 1 million construction machines manufactured every year. They do 10 billion hours of work. And we're really here to kind of take those hours and make them more productive and more efficient. We have this retrofit kit we put on 2 types of machines, excavators and wheel loaders. We're very lucky to work with a number of major construction equipment brands. So a few ones that are local here, like Hitachi, Yanmar, and Sumitomo. And what we do is essentially we take a camera, we take LiDARs, and we put them on the roof of this machine together with GPS, and we communicate with that machine to control its hydraulics. And that's made very easy with modern hydraulic machines because they have drive-by-wire control. So you move the joystick, it sends an electronic signal. We simply send the same signal to drive those machines. One of the kind of novelties and looking at the kind of academic work that we had was a lot of work around learning and AI and control in robotics. We essentially took that to teach this machine how to dig. So I talked earlier on in my presentation around that material complexity of the world, different stones, the melting wax. The Earth has exactly that, right? It's not the same. No matter where you are in the world, the Earth is going to be different. It's going to have rocks. It's going to be frozen. It's going to be sandy. It's going to have clay. It's going to have water. And the way that you dig in each of those materials is different. You can't pre-plan a tool path for how you dig a hole. You actually have to adapt as you're digging. And what we do is we essentially teach an excavator in simulation with kind of artificial soil. We give it lots of different ways of digging. We let it dig thousands and thousands of holes in simulation. And we teach it how to be rewarded if it fills its bucket efficiently. So you look at these 2 videos here where the soil is soft, it takes a deep scoop, it comes out with a full bucket. Where there's a stone hidden in the ground, it will actually feel across that stone and still come up with a full bucket. And this is something that's very hard even for a human operator to do because you don't have feeling in the hand. You have the sound of the engine revving up. You have the feeling of the machine lifting up. But here we're actually reading and teaching that AI to understand things like the pressure in the hydraulic system and to convert that to an understanding of force acting on the bucket and to then leverage that toward being able to operate efficiently. So we've deployed our systems in a number of environments. We're in 7 countries at the moment. We've been on more than 12 different brands of construction machines, so very versatile ability to adapt to those different machines. And we're doing a lot of repetitive tasks, things like screener loading, truck loading, pipeline trenches. But what we also see, if I look kind of back and tie in the work that I was doing with augmented reality and the way we communicate design, is that we've leveraged all of that 3D scanning information that kit provides, and we've exposed it to the operator. So rather than just saying, here's the plan, make it, we show the operator exactly what the robot sees. And they have this tablet we call Slate, and it takes the 3D scan that it produces. So it's every second it's creating a new 3D scan. And it's showing that to the operator, and it's everywhere where it's blue, you need to dig. Everywhere where it's green, you're on target. And everywhere where it's red, you need to fill. And so you can import a CAD model, and it guides you exactly where you need to dig. And the only other way that's done today is someone goes with a stick, and they check the height, and they spray paint, and then you go and you dig the spray paint away. And there's a lot of waste and rework and wasted time because of that communication. So the first core benefit of this technology is that it just shows an operator where they need to dig. But when they want to work efficiently, they can just select an area, press play, and the machine drives there autonomously, and it will dig and dump for them. So think of it as like a cruise control in your car. It takes over and it digs very, very efficiently. In some cases, we've shown 30% faster than an average operator. So this learning control gives you very consistent full buckets, gets the work done very, very quickly. At the same time, that augmented reality gives you a lot of awareness of other things. So for example, being able to show where buried utilities are. It gives you kind of X-ray vision of the world underneath you. Or if you're digging a hole autonomously and then needing to place some, here a precast manhole riser, you can actually use that georeference model to show you where you need to put that. So we don't do autonomous driving with a chain because it's very complicated. But we can use that same technology to show an operator where to put this. So where we're doing autonomously, we're adding productivity because we dig very quickly. But where we're not doing work autonomously, we're adding value because we augment the operator. So we're really trying to get that one operator to do work more efficiently across a number of machines. So the other great thing about this tablet is that it's portable. So you can use this inside the cab or you can take it away. And that gives the operator the ability to kind of learn robotics gradually. It's very difficult from day one to kind of understand how to use a robot. Here, we show the tablet inside the machine. They can use the machine as normal, but they have this wonderful 3D view that shows them where they need to dig. When they're doing a repetitive task, they can select an area, press play. The robot will go and dig there, just like cruise control or on-highway self-driving. And when they're kind of gotten used to that and the robot is just digging by itself for hours at a time, you can take that tablet out and have exactly the same experience monitoring remotely. So you see here, you can monitor the task, you can assign the area that you want the robot to dig, and the machine just digging for you again and again and again. When you have kind of multiple machines to manage, we also offer a joystick and pedal that plugs in just over USB to that tablet. So you can use the same tablet to remote control the machine as well. So you have augmented teleoperation, which lets you take over control from that autonomous system and drive it manually with exactly the same hardware setup. So we're able to transmit and then pass on that control from the autonomous machine onto this robotic system. And that lets you, for example, set up one machine to work autonomously, you set another machine to work autonomously, you manually drive another machine, you set it up, and you can check in and take control over multiple machines simultaneously with this one setup. Overall, the process looks a little bit like this. So you have this tablet we call Slate. It has an emergency stop button on it, so you can stop the machine whenever you want. You simply select the area to dig, you press play, you tell it to dump to the right or to the left, and if it wants to dump into a truck or into a pile. So if there's a truck, it detects the truck using camera and LiDAR. And you see here that same in-cab experience is what you have remotely, where you can essentially monitor and watch that job doing very, very repetitive tasks. So overall, I think, while earth moving in itself, it's the foundation of architecture. It's not really considered I would say, a high design activity. But it enables so many different ways of building. And if I look at the way that we've built this interface, it's really to let that operator, that person who's doing that job, understand and manage the kind of complexity, both of that material and of that kind of intelligent robotic systems. So, if I look back, almost not quite 15 years ago to my master's thesis here, essentially having this robot melt wax while showing me what was going on, while also handling that material complexity. This is also kind of what we're doing with the excavator, right? We're handling the material complexity of the world. We're exposing that robotic intelligence to a human operator, and we're giving them that visualization in the form of a tablet, which lets them intervene, which lets them take control, which lets them handle not just the kind of nuances of the soil, but also the nuances of a construction project. So construction is an environment where plans change every minute. It's not just at the whim of an architect, but it's also because you hit something in the ground you didn't expect, and you have to somehow adapt. And what we've tried to set up is an interface which lets operators do that and manage that very efficiently. So, yeah, that's it for my talk. Thank you all for coming. Cheers.